aspects of power dissipation. One is the static and another being the dynamic. And compared to the dynamic, the static is less, but no doubt loss is a loss. So still we consider the static power dissipation is also one of the power dissipation. And then we started with the interconnect, right? So nowadays, I mean, interconnect is nothing but what? A wire that connects any two transistors. And since there are more number of transistors, more number of interconnects or the wires are required. And wires not help in terms of connecting the transistors, but what is the other problem we have with the thing? Yes. What is the problem with these wires now? Advantages, we connect them, but what is the disadvantage?
Delay.
Yeah, it's they start contributing the delay. That is one of the problem is, right? So that's what we have. So now continuing with that particular delay aspect, okay? So what all the things this interconnects problem arises, okay? And the moment we have a wires, okay? So we should calculate the what is the resistance of that, okay? So all these things. Any wires between that there are some connecting transistors and all. These wires contributes the delay in terms of R and C. We should know what is the R value of this thing. Okay. So we started with previously. Just connect this. Yes, so continuing with the interconnect. So in the last class we saw what exactly we mean by the wires, and if there are two wires connected, I mean going parallel, so even we could find out what exactly we mean by the pitch. Okay, so we had two terminologies we defined. One is the wire pitch. Okay, one is the wire pitch. What is wire pitch basically is all about? Yes, it is the width of the wire plus the spacing between the two wires. So this is what the wire pitch is all about. And then we add one more terminologies that we studied, that is called the aspect ratio. Okay, the aspect ratio being, what is the aspect ratio? It is the thickness by the width of that. Okay, so these are all important now for us. So now the moment when you have this interconnect and what is this? See, all the designs are do happen with respect to the wire pitch and the aspect ratio. Okay, so these are the things that was do there. Okay. Now the moment we have all these things, there is another important aspect that you should know how to calculate the resistance of a wire. Okay, anything. So the wires are nothing but one of the layers. Okay, so resistance of a uniform slab or whatever. So how, what is the expression for resistance given by? What is the expression for the resistance of any wire given by? Rho L by, yeah, rho L by AVI. So rho L, what is this area is all about? It is the width multiplied by the thickness. Okay, so for example, if I call this as my width of the wire, okay, and this is my length. Okay. And what is this? We call it as, this is what we mean by the thickness. Okay. So the width into thickness is all about my area, and I have rho L by A. And what I call this rho by T as, yeah, what is rho by T? Okay, rho is the resistivity. Yes. Hmm? What is rho by T is all about now? This I call it as something like R naught into L by W, where R naught is given by the resistivity over the thickness. Hmm? And this R naught is nothing but what we call it as a sheet resistance. Okay? And the sheet resistance is unique for individual conductors. Okay, so for sheet resistance is different for the different metals. For example, gold has a different sheet resistance, whereas the platinum has a different sheet resistance. The silver has a different sheet resistance. Okay, so where R naught is rho by T is the sheet resistance, and as a unit ohm per square. Okay, so you mean to know that this thickness is with respect to the square now. Okay, so ohm per square. Okay, that is what the resistivity of it. And square is a dimensionless quantity corresponding to a slab of equal length and width. Okay, so that's what we mean by. Okay. Now, again, the moment if you know the resistivity, okay, I can find out what is my resistance. Okay, resistance is given by the sheet the sheet resistance. Okay, the sheet resistance multiplied by length divided by the width now. Okay, so if I know the length and width and the sheet resistance, I can immediately calculate what is my resistance. Okay, so in order to calculate the resistance of any particular layer or a metal, we go with these expressions. Okay, so these wires not only provide the delay, but they also gives rise to the crosstalk I said. Okay, the moment I have two wires which are close to each other, then there will be a crosstalk. If this is passing some information, there will be a crosstalk. That means it will in turn interfere with this now. Okay, so it will induce something into the other wire, and that's what we mean by the crosstalk. That's one thing. As well as we can see there is a capacitance effect coming between any two wires. So the moment we have an interconnect, we have a delay in terms of the resistance and the capacitance. We have a crosstalk. Okay, so these are the different aspects. The moment I have a RC, it is a delay, then the crosstalk. All these are the factor of or the matter of interconnect. Okay, so this is where we'll stop over this interconnect. Next, we'll go to something called one of the important aspects, that is the reliability. Okay, how much reliable is my particular device or a circuit? Okay, when it is operating, and that's what we mean by the reliability. So when I say the reliability, there are different aspects of this reliability. Okay, so the next thing, as I said, it is reliability. Okay, when I take up the reliability, okay, so designing a reliable CMOS chips involves understanding and addressing the potential failure modes. Okay, that means it is not that we build a circuit, but I should also understand if some natural calamity happen or something else, okay, happens, is my device is reliable enough? Okay, and that's what we mean by the understanding or addressing the potential failure models. Okay, so under the reliability, okay, a lot of things comes. One is the LachUp. Okay, so LachUp problem is LATCH. Then self-heating. Okay. Since the transistors are provided with, it is sourced by different potentials, right? And they are tiny in nature and they start getting heated, and that's what we mean by the self-heating. Can the devices withstand the self-heating? Okay, so that's what we mean by self-heating. And then electromigration. We'll see some of the aspect of this migration. Okay, electromigration. Then we have something called the odd carriers. Okay, odd carriers. Then we have over voltage failure. Yes, if there is some sudden over voltage from the main supply, okay, there will be some failure. How to overcome? How to model these things? Okay, so then something called the circuit pitfalls. Okay, so these are the different reliability aspect. Okay, that means we have to address the potential failure models. Okay, so how to overcome this thing. Okay. So first, we'll take up what is called the LachUp, okay, and that's what we mean by. Suppose in order to understand the LachUp, we'll take up the CMOS inverter. Okay, everything happens in terms of the IC. Okay, we'll take up the CMOS inverters. Okay, we'll just take up the cross-sectional view of CMOS inverter. Okay, so we have n plus if this is my P substrate. Okay, we have a oxide, then this is my gate, this is my source, and this is my drain. Okay, this is a P plus. This is the fourth terminal, and the fourth terminal of my NMOS and the source of NMOS are grounded. We know that, right? Then, if I want to have a inverter, CMOS inverter, it will have both NMOS and PMOS. On PMOS, I can construct the NMOS, but in order to have a PMOS, I need a well, and that is what this well is all about, right? Then I will have the P plus diffusion, and then the body is my N plus. Okay, so this is the gate outside, and this is my gate. Okay, this is my drain, this is my source. So this is the body. These two are connected to VDD now. And drain shorted. This is where the output we take. Gate and gate shorted, and this is where the input. So this is the simple cross-sectional view of. So this is my end well. Okay. This is what we have. Okay. If this was the case, it would have been done. So body is connected to VSS. We have some junction leakage. All these things have overcome. Okay. But even though we have taken care of secondary problems in this, but actually when this particular CMOS inverter, when it is operating, okay, there will be something that happens. Okay. What is that? Is what we'll try to see now. Okay. Now, can anyone tell me, is there any direct connection between this VDD and this ground in this particular circuit, in this CMOS inverter? Is there any direct connection from the VDD, which is at the rightmost of this cross-sectional, towards the VSS of the ground towards the leftmost? Is there any direct path? Pass. Can I see any direct path? No, right?
No, sir.
Yeah. Now, if I just see this particular circuit in a close aspect, okay? Now, what are these junctions in the N well? P plus, right? This is P, this is N, and this is P. What is happening here? What is this P N P means what? Have you come across any thing like PNP. What is this PNP is basically? I have a P region, I have an N region, and again I have a P region, which are connected back to back. What it forms? Transistor, right? Transistor. Okay, see, and that is what we are having now. Okay, so you can see that this is my P, yes, this is N, this is P, this is P kind, this is N kind, this is P. All of you are with me? First, so I have one BJT, that is PNP BJT, that is existing where in the from the N well up to this P substrate. Okay, so P, N, and P. Similarly, there is a transistor or a kind of BJT. See, this N plus and this N plus. This is N. This the substrate is P, and again I have an N here, right? So this is N. Yes. This is N. This is P, and this is N. Is that okay? Is this clear? Fast. And this P and this P are same, so that's why they are shorted now. All of you are okay this till this point? Fast.
Yes, sir.
Okay. So we are having a two BJT existing within this particular CMOS inverter. Okay. From the NMOS, we have an NPN, that is a from the NMOS we have an NPN, and from the NWell we have a kind of PNP transistor. Okay. And now if I just have this substrate, okay, since the substrate will act as something like a resistance, right? So I can have, this is the resistance offered by the substrate. Okay, this is P. In between this is what I have. Similarly, I have a resistance offered by N well, and that is nothing but what? It is the resistance with respect to well, and this has to be going in parallel with this. Hope this is fine. Yes, this is what exactly the connection will get. So there will be a substrate resistance offered by the wafer, and there is a N well resistance offered by this, that is nothing but what R well, and there is a kind of PNP BJT kind of transistor existing between the PMOS and the P substrate, and there is an NPN kind of BJT formation between the NMOS and the N well region. Yes, hope this is fine now. Fast. Yeah, so now what I'll try to do is I try to write this particular circuit in the other way now. Okay, so now I'll just ensure that my VDD is at the top. Okay, this is my VDD. Okay, and at the bottom I have the VSS. Okay, so whatever the cross sectional you are seeing, okay, I have this horizontal version I am writing in terms of vertical. Okay, so VDD is my right, that I am pushing to the top. VSS or the ground is at the left, that I am pushing at the bottom. Okay, I'm just doing a 90-degree shift left. That's it. Okay. So now if I see that from VDD, okay. So instead of okay, so instead of taking this path, what I will do is I'll take something like this. Okay, because I am interested in the VDD and also the ground. Okay, so because I just this one change. Okay, it is not from the drain P region, it is from the source P region. Okay, so this is one change that is there. Okay, or I will do that in by erasing that. Yeah, and this I just use this. Okay. Yes. Okay. I'll just put this. Yeah, this is what happened. So from VDD, there are two parts. One is the resistance that I'm seeing, that is the R well. Okay, this is what. Okay, so this is my R well. And another path is the P type, right? Okay, so from this VDD, I am tracing two paths. One is the P type, okay, and another is the R well, and that's what I'm having. From VDD, I have one R well path, and from VDD, I have a P. Yes, and this is my P type. This is N, and I have one more P. Yes, and this R well is connected to an N type. Okay, and then this is N. This is my P, and this is N, and that is going. So now through ground, I have one N region, and that is what my ground is all about. One N region, and another path I am getting is my R substrate, okay? And that is what I have my R substrate. This is my R substrate, and this is what. And you should know now that this N and this N is common. That's what this N and this N. This is what my 2N. That is this is N common, and this is PP. This is P N P. This and this P is common. This is what the equivalent circuit I get with respect to the VDD and VSS. Okay, that means there is a connection between this. Hope this is fine now. Okay, we are interested from the VDD to the ground. Okay, we are not interested in the gate region as well as we are not interested in the drain region. So this is what the equivalent that we have. Is this clear till this point? Yes. Fast. Yes. No. Yes. And this automatically ensures that, okay, I'll just take the one, we have one NPN transistor and another we have a PNP transistor, right? And if I just look into my an NPN transistor, okay, you can see here, this is my NPN transistor whose emitter is connected to the ground. Okay, that is VSS, that is zero potential. Yes. This is base kind of, this is emitter, and this is my collector. Okay. So in order to exist, or in order for the base current to flow, what is the condition over here? In order for the base current to flow, what should be the condition over here? Yeah, a simple NPN transistor, common emitter configuration. Yes.
Base emitter forward bias.
Base emitter should be forward wired, and I want minimum of 0.7 volts for the IB to flow, right? So my base to emitter potential should be minimum 0.7 in order for IB to exist. Okay, and then emitter is common. I can say IC is beta times of IB now. Yes, it is a common emitter configuration. Common emitter configuration, I can use it for a what? As a switch, or as an amplifier, or as a voltage follower. Fast. What is really happening here? What is your beta value? What is the beta? What is
Amplification.
yeah? It's an amplifier. Beta is greater than 1. If I assume simply beta is equal to 10, if my IB is equal to 1 microamperes, okay, my IC will be 10 microamperes. Okay, it is that kind of thing. Is that okay? Yes, no. Yeah, there is one more thing. This is not an emitter here. It is just a path here. Okay, so this is a PNP. I'm just drawn in the wrong way. Okay, so just try to write once again the next one. Okay. So we have something like this now. This is my VDD. Okay, I have two paths. One with R, well it is, okay, and another with respect to my P. This is P, this is N, and then I have one more P, and then I have a VSS here. VSS has two paths, one with respect to R substrate, and another is with respect to my N. This is what we have. This is what. Okay. And this is my NPN transistor, whereas this is my PNP transistor. Just now we saw if this particular voltage, that means voltage, if I call this as something like node A and I call this as something like node B. Node A is nothing but what? The base to emitter voltage. Okay. If this is something like 0.7, okay, here the collector current will be simply a beta times of IB. Okay. And now this is the NPN transistor. Now I'm going with the PNP transistor, right? P, N, and P. And P is connected to what? VDD. If I assume VDD to be something 3 volts, now tell me what should be this base voltage here in order for the base current to be on fast. In order for the base current to exist over here, what should be the base voltage over here? It is a PNP transistor and your emitter is connected to VDD, and I am giving VDD to be somewhere around 3 volts fast. Yes, I have already given the int with respect to NPN transistor, NPN, and here the emitter is at ground. My base voltage should be 0.7. Okay, that is minus. Come on, what is minus? With respect to VDD, you tell me. Here, emitter is at ground potential. What was the base voltage that I should apply in order for the base current to flow here? Fast. What was the base voltage that we apply, minimum to apply, in order for the base current to flow in the NPN? I've already written. Tell me what is the base voltage that we should apply when the emitter is at ground potential?
0.7.
0.7. Now, for an NPN, the other way, right? Emitter is connected to VDD, that is 3 volts. What should be the base voltage here?
3.7.
Huh? Come on, this is stupidity, right? No. It's zero. Unbelievable answers. Unbelievable. So for an NPN, emitter is 0. We try to increase the base by 0.7. For an PNP, if emitter is at VDD, or I am giving the voltage to be 3 volts, in an NPN we increase by 0.7 with respect to emitter, but for a PNP, we will be increasing or decreasing the base voltage in terms of 0.7. We have to decrease, that is, we have to apply somewhere 2.3 volts at the base in order for the base current to flow. Is that clear with everyone? Yes, this is the another way of analyzing your PNP. What should be the base voltage if the emitter voltage is given? Yes. Why this has not been taught in your third semester? Hello. For an NPN transistor, emitter is at some positive potential. Yes. My base. Now you tell me what is VBE now? VBE is 2.3 minus 3. What is the base to emitter voltage now? Is it now minus 0.7? Yes or no? Fast.
Yes, sir.
What is the stupidity happening with you people now? For an NPN, your base emitter should be forward bias in terms of positive 0.7 volts VBE. For a PNP, VB again it should be 0.7, but it is the reverse. It has to be minus 0.7. Yes or no? And since my emitter is at 3 volts, my base voltage should be at 2.3 in order for the IB to flow in the PNP transistors. Is this clear now? Yes or no? I mean, if you can't understand this simple basic analog theory, I think it's very difficult. It's very difficult for your, I mean, I don't know in what kind of job you fit and all. I think that's why most of you want some software job and just end up in getting some earning some money, right? Yeah. At least you should be in a position to know that the base to emitter should be 0.7. If it is an NPN, it should be plus 0.7. If it is a PNP, it is minus 0.7. How to get a minus 0.7 between VBA? This is what my VBA, right? This is my VBE. And in the similar way, this is my VBE. Base is at positive potential, ground is, and the emitter is at negative potential. Here the other way now, plus and minus. So that's why VB you get minus. Hope this is fine. Hope this is fine.
Yes, sir.
What, sir? I don't know. Okay. I repeat once again these two things. Okay. For an NPN transistor, an amplification thing. Okay. Emitter is somewhere grounded. This is my base, the collector, then the emitter. Okay. This is what we mean by base to emitter voltage. And the minimum base to emitter voltage that should be there is 0.7 volts. Since emitter is at ground potential, what should be the base potential in order to have VBE to be somewhere around 0.7? Common sense. This is 0.7 volts. What is VBE? It is VB minus VE. VB is 0.7 minus V is at 0, so it is again 0.7 volts. Similarly, I just asked you people, okay, if I have an NPN transistor, sorry, PNP transistor, where emitter is connected to VDD, okay, this is my collector, this is my base, and this is what we mean by the base to emitter. Yes. And since this is P and this is N, and here it is something N, P and N, V has to be connected to positive, N is connected to negative or ground, that is okay. But here is what? N should be connected to what? Negative. P should be connected to positive in order for the forward biasing. And in order to forward bias, what is again the VBE should be 0.7. And how to get the 0.7 at how to get 0.7 VBE? Just to make sure the base should be at 2.3 volts because VDD is at 3 volts. I've already given that 3 volts, right? Now you take VBE. It is VB minus VE. But VE is at positive potential. This is V plus. VB is at negative potential. This is what? So it is minus 2.3 plus point something like 3. It is again 0.7. Again it is 10. Is that clear? This is how we will be going with. Now, having said and done, we are interested in this particular circuit, right? Yeah, that is very crucial now. How it is crucial, that's what we will try to see now. As said, node A, right? This is my node A. Okay, because of some noise, some jitters, okay, something, assume that node A, because of noise, node A potential rises to 0.7. Okay, now tell me, there will be base current existing or not in this particular NPN transistor. Fast. Fast. Yeah. Yes, right. The moment there is a base current, and again you assume that there is 1 microamperes of current, and beta is somewhere around 50. What is the collector current now? What is the collector current here? What is the collector current? It is 50 times 1, it is 50 microamperes. That means there is some base current that is existing. Okay. This is the collector current. You can see that again. This is my IE. Okay. Emitter current is equivalent to collector current plus the base current. This is what is happening. Yes. So this, whatever the collector current now arises, and since there is a resistance over here, assume that the drop over here and VDD is somewhere around 3 volts. By the virtue, this base current is sufficient. Sorry, the base voltage here is sufficient for the base current of the PNP to transfer. Again, this will be in terms of amplification. Again, I can see this is the collector, and this is nothing but what? Beta times of IB. And IB is what here? IC of NPN is equivalent to IB of PNP. So this is nothing but what? Beta times 50 microamperes. Beta is how much again? 50. 50 into 50 microamperes. That means the voltage here keep on increasing. That means there is the multiplication of base current, right? Because of the base current existing at the NPN, there will be collector current. And that collector current is nothing but what? The base current here. And because of this base current, there will be increase. So it is nothing but what? The base current of NPN is giving rise to the collector current of NPN. And the collector current of NPN is nothing but what? The base current of PNP. That is giving rise to the IC. So if this is 1 microamperes, this is 50 microamperes, this and this are same, and now suddenly if this is 50, this is 50 into 50. So it is almost 250. 50 times the 50, right? 50 cross 50 microamperes. And the moment this IC is nothing but what? Again IB over here, again there will be a multiplication factor. That means I will have a current path. There is a path from VDD to ground existing. Yes, this is what the kind of multiplication of current that is happening. And why this multiplication is happening? Because of what? Why this multiplication is happening? And we call it as something like a multiplier circuit also, this LachUp. Yeah, why there is a multiplication happening here? Yes. What is the phenomena that is involved in this particular circuit now? Yeah, there is a positive feedback kind of thing. Okay. Because of that, there is a multiplication. That means increase that is happening now. Okay. So this ensures that there is a path directly from VDD to the ground, and that's what I asked you initially. Okay. In this particular okay, so if I go in this, Yeah. So I said initially we could see that there is no path existing between this VDD and this ground, right? Yes. But because of this transistors existing along with this resistance, there is a path connected from VDD to this VSS, and this there is a current flowing from VDD to the ground here, and because of that, there is a reliability issue that is coming into concern now. Okay. So I have to ensure that I have to minimize or I should overcome this latch-up problem. Okay, so I don't want this latch-up thing to happen here. I should ensure that the latch-up is overcome. So now, how to overcome this latch-up problem? Yes, how to overcome this latch-up problem? Okay, before I go with that, hope you understood what is this latch-up problem is all about, why this exists, and what is the implication of the latch-up? Yes, no. Fast.
Yes, sir.
Yeah, no doubts. Okay, good. Now, as I said, this was VDD. This was my RWell. This is my P, NP, and this is where I add my VSS. It's a ground here. This is star, and I am NPN, and this is what we have. We add for this as A, this as B. Yes. This is P, N, P. This is N, P, and N. And the base current here and collector current. This is IB. Okay. This is emitter. This is my IC. So this is how exactly. So again, if you see anywhere, my IE is combination of IB plus IC, whether it is in PNP transistor or it is in NPN transistor. Okay. The collector current of PNP is acting as a base current here, and because of the base current of NPN, I have a collector current, and this collector current is nothing but what the base current. Yes, and as I said, because of noise, if I assume that there is a 0.7 volts at this point, and there is a base current appearing, and if base current is somewhere around 1 microamperes, and if beta value is instead of 50, I'll just take it as something like 25. Yes, the collector current will be simply 25 microamperes, and this acts as a base current for the NPN. Yes, sorry, PNP, and this in turn gives rise to 25 times 25 microamperes base current for an NPN transistor. Okay, that means I have a path now, right? This is what it multiplies, keeps on. Now tell me how to overcome this latch-up problem, how to minimize this multiplication aspect. Fast, simple thing. Yeah, how to minimize this? How to minimize? The int is there in the circuit itself. How to minimize? How to ensure that the voltage at this point, okay, or voltage at this point is very minimum, almost zero, you can say. Yes. What to do in this circuit? Yes, exactly. So this is my R sub, right? I keep on decreasing this. Minimum, 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 minimum. What is the highest minimum I can get? Can I short this? If it is, if I make this R sub to be very minimum means, if I make the resistance of this 0 means what? Is it a kind of short circuit? Yes or no?
Yes, sir.
What is the short circuit voltage you get? 0. The moment I have a short circuit, there is no voltage that appears at the base. Okay, that means base is at also 0 potential. My emitter is also at 0 potential means virtually I'm saying eventually my base to emitter is 0 voltage means this is off. The moment this is off, there is IC is 0. The moment IC is 0, the base current of this PNP is 0. That means there is no path from VDD to VSS. Is this clear now? So ensure your R sub and R well is very minimal. Okay. The moment I have least resistance, I have voltage drop to be almost 0. At that particular instance, I can ensure that there is no base current flowing in any of this transistor means there is no connectivity between the VDD and VSS. That means there is no reliability issue. Yes? Hope this is fine. Yes? And there are some methodology, okay, how to minimize the resistance in this substrate and the well. Okay? There are some mechanism how to minimize the resistance, but if the moment I try to reduce my resistance, the substrate resistance or the end well resistance, I can ensure the LachUp problem can be worked up. This is one of the method of that. Hope this is fine now. I should ensure only this now. Okay, I should ensure. Okay, yeah, this resistance should be minimized, and this resistance should be minimized. The moment I minimize these things, okay, then I won't be having a connection between the VDD and VSS. Okay. This is nothing but what? A short kind of, right? More power dissipation, more eating. Okay. This is one. This is what is all about your LachUp problem that exists in an IC, especially in terms of the CMOS inverter. And CMOS inverter itself is the common. This is the CMOS inverter is the basic building block for any of the MOS transistor, right? And that's why they ensure that the LachUp problem is overcome. Yeah, so this is what I wanted to tell you about after the interconnects. That is the reliability aspect, that too of LachUp problem. Any questions, clarifications? I'm happy to get that.
Sir,
Yeah.
reducing R will have any improvements here, sir?
Reducing?
R well, we have reduced R sub so that it's minimum. R well, can we reduce to make it minimum so that there is some.
That's what I'm saying, right? That's what. There are mechanisms. Okay, so there are mechanisms in order to reduce this R sub. See, the moment any one of the transistor is off, eventually all the transistor is off, right? Yes. N will leave it. I will try to reduce R sub now. Yes.
Okay.
Okay, because I have P substrate I have taken. Okay, I use some mechanism to reduce the resistance of that particular P substrate. The moment I make it minimal, ensuring that the base current over here is minimum or it is almost 0. How it will be 0? Ensuring that this voltage is almost 0. Yes, I can do that. By reducing the R sub, I make sure that this voltage is at 0 potential. The moment this is 0, IB is 0. In turn, the collector current or the base current for this becomes 0. That's it. The moment the BNP base current is 0 means automatically, even though if I have not reduced my R well, okay, that is still no problem for me. Yes. I have to ensure one transistor is off. That's it.
Okay, sir.
Yeah, I can reduce R sub and ensure the transistor doesn't conduct. That's it. Yeah. So if someone is having doubts how come this resistance has come into a parallel, I'll just draw and show you. There is nothing like a big deal in that. Okay. Okay. So this is, I'll just show the N well here. That's it. Okay. This is my N well. This is P plus. This is P plus, and this is N plus, and this is drain. I said this is source. This is where my gate comes. Source of N and sorry PMOS. This is going to VDD. I am interested in the path between VDD and ground, so that's why. This is what my P. Okay, this is P. This is N well, right? This is N well. This is P. That's what. And instead of writing in the vertical, I'm making it. This is P, N, and this is my P. This is, and that is where this was conveying in parallel with this. Hope this is fine now. In the similar fashion, how we add this? This is P plus, this is N plus, this is N plus. These two were went to the VSS. That's why I was interested in this. Okay. N, P, and N. This is N. Make sure that this N is shorted over here now. Okay. This is P. This is P. This is shorted. Okay. Okay. Just to make sure that how this was parallel here. Okay. I'm ensuring that this is also, so my R well is connected to the base of PNP. Similarly, my R sub is connected to the base of NPN, and this is what we know. This is my R well. This is, sorry. This is what R well is connected to the base here. Similarly, R sub is connected to the base of this. Okay. Okay, is that clear now? Just I'm ensuring that how exactly this goes. Okay, there is no big deal in this. I'm just interested in the VDD to VSS. Okay, so P and N, there forms two paths, one with respect to the P type from VDD and another path I have through R1. Similarly, from VSS, I have one path through R sub and another path to the N terminal of the NPN transistor, and then you know how the base of this is connected to other symbol. Yeah. Yes, any clarifications? If no clarifications,